Good morning and welcome to Team Problem Solving. What we'll be talking about today is using the A3 format for moving through any problem which uses the PDCA, Plan, Do, Check, Act methodology to identify an issue, identify a problem, and walk us through, hopefully, to a good solution. For those of you that are joining me with Teams, this is just a general way of doing things, but if you hover over the screen, you'll pick up a menu which will allow you to mute yourself or to type in questions. So I encourage you, if you have questions as we go through this, to type them into live Q&A dialog box, and we will try to answer them as they're presented. Key points for success in any problem solving. The principle is respect for the people, respect for the individuals doing the work. Change should not be a nuisance. Data-driven decision making to implement change for improvement should be considered a normal part of the everyday job responsibilities. Many of us view problems and changes as issues that we try to avoid. By using this A3 process, what we're going to do is try to attack these issues or these problems and seize on those opportunities to make the working atmosphere better. Some simple things to think about is trust and believe in yourself, take responsibility, be committed, identify opportunities, make the opportunity visible, and lastly, eat the cake one bite at a time, and that is, don't try to take on a huge problem because all you're going to do is break it into a lot of smaller A3s. So let's kind of view this as taking one A3 at a time, small bites of the problem until we get it resolved. The objective are going to go through these 8 steps, and these are our normal Plan, Do, Check, Act type processes that'll take us again from the opportunity to the final improvement. Why change? There's a myriad of reasons, but the one is primarily quality, productivity, inventory. The one change that we all need to do is to try to get better and try to get the working atmosphere better. A little cartoon here, and it kind of drives home this point of when we see a problem, how do we react to it? If we see a sink overflowing, what's our first reaction? Is it going to be to clean up the floor, or is it going to be to shut off the faucet? And quite often people spend too much time mopping up the floor and never solve the problem. Typically we call these people firefighters. So as we go on, opportunities are tasks where the outcome is not predetermined. If you know the answer to an issue, if you know the right way to be doing something to solve a problem, I encourage you to just do it. This is a methodology where we don't know really what the solution to the problem is. And if we follow this methodology, it'll take us to a good root cause analysis and a root cause solution. And part of the way you'll know if you got to the root cause is once you solve the problem, it won't come back. If you find yourself in a position where you keep firefighting and resolving things, but then they always keep resurfacing, it's usually because you didn't get to the root cause. All you've done is put out a fire. Is problem solving part of your job? I encourage you all to think about that and also think about the people you work with. But I believe problem solving needs to be considered part of everybody's job, but it shouldn't be a nuisance. It needs to be something that is encouraged and supported and allow people to experiment to try to get to a better position. You've heard me talk about the Plan, Do, Check, Act methodology, which was commonly referred to as the Deming cycle, as Deming introduced that at Toyota many years ago. But it's basically Plan, Do, Check, Act. And The planning stage of this is a big part of what we'll talk about in the A3, and that is truly defining and understanding what the problem is. Doing is trying to experiment toward resolving the issue. Then finally we have check, did we actually solve the issue? And then adjust, how are we going to sustain it so that it doesn't backslide? It begins with identifying the opportunity, where are we now? And we're going to talk a lot about how do we formulate a problem statement. Then where do we want to be? And that's part of the target statement or the future state, and how are we going to get there? And then finally, the experimenting stage of how do we implement these changes. And I'm going to encourage us to investigate looking at single variable experiments rather than trying to a shotgun approach with a lot of different things happening at the same time. A little example of a problem. I don't know if any of you have ever worked one of these pencil mazes, where it's a maze and you kind of know where the start is and you know where the end is, or the finish. And how do you get through here? How do you navigate this? Well, my first exposure to this, I would just try to do a trial and error, so that I just would keep going through, bumping my head on a wall, but keep going through until I got to the final end of my, my problem to try to get to the finish point. Is that a very efficient way to do it? Probably not, in that it takes a lot of time and a lot of resources before you get to the final point. If you begin studying the line or studying the maze and trying to visualize and experiment visually how to get through to the end, typically what you'll find is you could navigate that a little bit faster and a little bit quicker, and you'll get to the end and have success. But again, is that the most efficient way to get through to the end? And what we've found is that if you incorporate a team or incorporate more than one person, typically what happens is, as a team, new ideas will surface, new ways of approaching this will surface, so that you can get to the end much quicker and much more efficiently. That's the essence of team problem solving, rather than just dumping it on one person and have one person solve the problem. The essence of team-based problem solving is to get there the most efficient way, but get to the ideal solution. Many times, if we're single or just one person working on a problem, we put a lot of self-constraints on ourselves. Things that have happened over the course of our lives, and now we've concluded that we're not going to change that. This is in our brain, it's in our DNA. An example of that would be something like this. This is just an exercise or a little experiment in self-constraints. But people look at this, and if I were to ask you to look at this, you all know what it is. How would you change that to 6, for example, by adding just one more line? And do the self-constraints stop you from getting there? So I don't know if any of you have any thoughts or any ideas, but do you think there's a way to do that, to add just one line to get that to be a 6? And probably the answer would be this, adding an S. Now, many people won't add the S because the perception is it has to be a straight line. And that's a self-constraint. It's not a constraint I put on the team. It's a constraint you put on yourself as you look at those types of things. As you begin to become more comfortable in working in teams rather than as an individual, you'll find that you can get past these self-constraints much faster and much more meaningful results. So the first part of an A3 problem-solving methodology is to determine what is the actual problem. And an effective problem statement contains 3 things. Where is it happening? Describe the process. What is happening? Identify only one problem, and how much is it happening? If possible, describe it with numbers or metrics. You could do a percentage, time, effect, but somehow how much is it happening becomes very, very important when you're trying to measure, have you improved it? So this is an example that I'll show, and then I want you thinking in your own terms about a problem statement. Sample problem statement could be, where is my car? What's happening is it's using more fuel, and my mileage has dropped to 10 miles per gallon. So basically what I'm saying is my car is using more fuel and my mileage has dropped to 10 miles per gallon. The critical part of that is I'm not blaming anybody. I'm not coming up with a solution. All I'm trying to do is describe what is the problem. We as a society, unfortunately, have a real hard problem doing this. We typically want to describe a problem as what is the solution. So we don't want to do that. We want to just identify in as objective a fashion as possible what is the problem. Identifies one problem, non-blaming, does not state a cause or a solution, real numbers, quantified, clear, concise, in as few words as possible, rather than getting into a lot of verbiage or writing a book. All you want to do is concisely say what the problem is. So, current condition. If I were to show you this as our current condition, and this is the sink overflowing, it's a horrible picture, I apologize for that. But the sink overflowing, how would you describe that as a typical problem? And so as an exercise, let's think that through. And maybe all of you can kind of think in your own minds, what would that problem statement look like? Where is it happening? What is happening? And how much is it happening? As you think that through, I would like you to, if you have a little piece of paper, sketch out what you think a problem statement would sound like. Again, it's not non-blaming. You're not blaming anybody for the sink overflowing. But where is it happening? Well, typically it's happening at the sink. So once you identify where it's happening, then it's what is happening and how much is it happening. And it's pretty hard to apply numbers to what you're looking at, that it's overflowing. So when you're in a situation like that, we need to be a little bit open. By the way, on the screen right now is a typical A3, and they're called A3, and this is the A3 format simply because of the size of the paper. Typically, these things were put on an 11 by 17 piece of paper, which is typically called an A3. And the reason they did that is because they wanted to tell the entire story on one sheet of paper. We didn't want to have a lot of different pieces of paper telling the story. So one piece of paper will take the problem statement all the way through to the solution. And that's how this is presented. So in our problem statement, where is it happening? At the sink. What is happening? Water is leaking on the floor. And then finally, how much is it happening? Pretty hard to put a number together for that. But one of the things that we do know is while the water is leaking on the floor, we're losing productive time. So while we haven't identified how much productive time we're losing, we have identified what is the metric that we're going to be looking at to evaluate whether we're improving the situation or not. So to define the problem, there's a lot of different ways to go about it. This is a value stream map which could be used. This is a layout and a spaghetti diagram which could be used. This is a process flow diagram which includes the decisions that have to be made. There's a lot of different ways to grasp the situation and define how much of a problem it really is. So if you're grasping the situation, check sheets are a very, very, very useful tool. And the reason they're useful is because they should be structured that whoever is gathering the data, all they have to do is put tick marks or check marks in the boxes rather than do any mathematics or any calculations. These are both different types of check sheets. This one would be for telephone interruptions. This is one for production output. A control chart is a little bit different in that you just put a dot on the chart at the proper levels as you're running it through the day. Using a control chart, though, you're able to calculate what are the upper and lower control limits and what is the quality impact of what you're looking at. But in our case, when we looked at the sink, this is the check sheet that we finally got to. And this is a check sheet, a reason for downtime at the sink. Low water level, refilling the water, overflowing the water, mopping the floor, or other issues. So if we're looking at this, we'll note that 6 times the water level was low. If we wanted to refill it, we had to refill it 42 times to prevent it from getting low or to correct it for when it was low. Overflow 13 times that we actually overflowed the sink because we didn't shut it off in time. Mopping the floor, we had 12 occurrences. So when you look at a chart like this, it gets a little difficult, especially when you put it on the A3, for somebody to read that and make sense of it. So typically what we like to do is to take that and put it into a more visual form. And in this case, this visual form or visual communication tool for this could be a Pareto chart. So for those of you who aren't familiar with a Pareto chart, it's basically visually showing you an 80-20 rule, in that 80% of the time or 80% of the problem is caused by 20% of the issues. So that what we want to look at is how do you build a Pareto chart. So this was the data, 6, 42, 13, 12, 4. Total stoppages were 77. So in building a Pareto chart, you have an x-axis, and that'll be the type of issues that we had, and a y-axis, which is going to be how severe were they. So the effects and the types. In the types, we have refill, overflow, mop, low water, other. In the occurrences, we had 77. Why did I pick 77? Because 77 is the total or total occurrences that happened during the time period we looked at. So this is not just an arbitrary number. What you do want to do is have the full population of what you observed up here. And to fill in the rest of it, just 77 divided by 2 and so on, and that's how you determine these 3 areas in addition to the 77. And then just take the data from the check sheet. We had 42, I think it was, refills. Overflows were lower. Mop floor was lower. Low, lower. So that we take it from the highest or the most severe issues and work it down. We then have a 100% on the right side axis, which tells us this was probably maybe 60, 65% of our problems. These don't have to be precise. And we graph that to make sure that we've included 100% of the issues of what we're looking at, which correlates to this 77. When we look at this, it tells us that probably refilling the water is occurring more often than anything else. And mopping the floor is the third item that we're concerned about. But this is not a visual display of the downtime. This is a visual display of how often it's occurring. To get the downtime, we would have to, this is that Pareto chart as it would appear in Excel. Excel, by the way, is a great tool for creating Pareto charts. It's an automatic thing. As you populate the data, it'll create the Excel sheet or Excel chart for you, Pareto chart. So we have a problem statement at the sink, water is leaking, losing productive time. Then we have, as we got into here, we have a Pareto chart, but it really hasn't told us the full story because it's not measuring productive time, it was measuring occurrences. So to expand on the number of occurrences is how long did each of those occurrences take? Now we have a total downtime of 123 minutes, again split into these categories. And again, we could build a Pareto chart showing that so that we could visually communicate it. But now we've learned that mopping the floor is the larger issue that's happening because it's taking 60 minutes of downtime. Without the Pareto chart, you would just be putting this chart on the A3. And again, this chart becomes a little more difficult for people to read and interpret. This becomes a better visual tool to show, yeah, we're going to focus on mopping the floor. How can we reduce mopping the floor time? Because that's going to have the biggest impact on us improving this situation. Again, it's a check sheet, or you could have run charts. There's a lot of different ways to display the data or display the information, but what you want is something that's very visual. By the way, this visual representation, which shows a big dip and a big dip in productivity, is actually machine 1, which if you looked at the numerical value for machine 1, it doesn't become as clear as a visual representation will. Another tool is a histogram could be used, and again, this summarizes maybe 50 to 100 data points. Histograms are not very valuable unless you have a lot of data points. But typically, you're trying to establish, do you have something that's in control, and in control will be a symmetrical bell curve. But the first thing to look at is how does that bell curve compare to the customer spec? Is it centered on the customer spec, or is it skewing to the right, skewing to the left? Is it bimodal in that there may be 2 occurrences, 2 shifts, for example, could do this, 2 different shifts running. So part of it is you want to get a symmetrical histogram, and if you don't have one, this becomes a clue as to what you need to do to improve the process. Another is sub-process mapping, which looks at what are the process steps, what are the decisions that have to be made, and what is the final outcomes. And as you go through this, a sub-process map, the basic way of performing one of these, although they do go vertically, is from left to right, start, finish, with a process in the middle. This is an example of a process map for repairing a flat tire, for example. We've all had a flat tire. Driving the car in, remove the tire, soak the tire, fix the leak, pump the tire up. Is the leak fixed? Becomes the question you have to ask. And the red line here, which is the no answer, if you had to answer no at that point, this becomes the rework loop. And the rework loops are what you want to identify in any process, because these rework loops, as you eliminate them, it makes the entire process more efficient. So we do want to identify where those rework loops are. This would be another example of using swim lanes if you have multiple processes going on or multiple people functions going on. This is the customer swim lane, this is the salesman's swim lane, this is the detailer, and this is the documents, any paper documents that have to be used to support the process. Again, it's just a good visual way of explaining what's going on and what does the process really look like. In this case, walk into the store, locate a suit, try on a suit, and when you get to this point, talk with the salesman, talk with the customer. Now you have a parallel process going on. Both things are happening at the same times. The salesman is now going to mark the suit up. The person removes the suit, and the customer or the salesman will take the suit. The salesman writes out a receipt stub, which he gives, and the customer leaves the store. And then the salesman goes on to pass it on to the tailor to get the adjustments made to the suit. When he's finished, it comes back to the salesman, who then calls the customer to say, we're done. This is just a way of separating. Instead of just stringing all of these things out, it's a way of separating who has to do what and when they have to do it. And many times, if something is happening in parallel, if one of those people aren't available, that's going to cause a delay and less efficiency in the process. So getting back to our A3, which again, putting it all together, this is how we communicate, and we want to post this on a wall someplace so everybody can see it. The first step is, what was the problem statement at the sink? Water is leaking, losing productive time. The next thing is, how do we study this problem? And it could be a layout showing a spaghetti diagram of all the movements that people have to make. It could be a process diagram showing what are all the steps in the process and what are the decision matrix for getting to the end of this process. Or it could just be Pareto charts trying to illustrate this is why we're focused on downtime and this is what's causing the most downtime. Finding a root cause is not that easy. Many of us, probably when we were kids, very young, we probably were better at identifying root cause than most people are today. And most people today want to jump to a solution. They want to jump to what they believe is going to be the answer, rather than really diving into the issues and trying to find out what is the true root cause. But to find the root cause, we need a clear and complete problem statement, which I went over. We need to observe and study the process, get data, get real data. A lot of times pulling data out of historical data, out of databases is not a good approach. Much better, if possible, to actually observe what's going on. And then we're going to talk now about cause and effect diagrams and how do we assign root cause. For many of you, I'm sure you've seen this diagram, which is called a fishbone diagram, or Ishikawa was the first guy who started using this, so it's called an Ishikawa diagram. But basically, it looks at what is the problem statement that's going on, and then starting to assign causes based on these 6 criteria: manpower, method, machines, materials, measurement, or Mother Nature, or the environmental conditions around what the process is. I'm going to go over an example of this. Maybe some of you have seen this before, but if you haven't, it's a very good illustration of using this Ishikawa or 5 whys analysis to get to what is a root cause. Excuse me. This is a problem statement, and this is not a fictitious problem statement. This was actually happening, and it was documented by Lee Jenkins. The concrete on the Jefferson Memorial in Washington, D.C. requires repair every month. Future state target was stop the Jefferson Memorial from crumbling. So that's our future state. That's what our target is. But before we can get there, let's identify what the root cause is. So the problem statement will go in here, which is the concrete on the Jefferson Memorial requires repair. So when we look at that, why was the memorial crumbling? This is just an example, and I want you to think this through with me as we walk through this. Why was the memorial crumbling? Because it was cleaned twice a week with a soap solution that was causing erosion. So where does that belong? Which of these 6 causes or reason codes should it go with? And I think most would agree it probably goes in the methods section. So that clean twice a week is really falling under the methods part of this. So why number 2, the second why? Why was the memorial being cleaned so often? And because there were a lot of pigeon droppings on the memorial. So that's why they had to clean it twice a week. So when we start thinking about that, because there were a lot of pigeon droppings, that's not necessarily a method. Maybe that falls under here with maybe Mother Nature or the environment. Why number 3? Why were there so many pigeons causing this issue? And the answer to that was because the pigeons are attracted to the spiders. There were a lot of spiders on the Jefferson Memorial, so the pigeons were coming there to eat the spiders. So again, is this a manpower, method, machine? No, it probably also falls under that Mother Nature or an environmental issue. Why were there so many spiders? Kind of, you're getting the gist of this, where we just use the answer from the previous one to create the next why. So why were there so many spiders? Because the spiders were attracted to the midges. Midges are these little flies that spiders like to eat. You won't find them in raisins or anything like that, but they are around. So when they're there, pigeons love to eat them. And again, I believe that's a Mother Nature or an environmental issue. And then we get to why, 5 whys. Why were there so many midges? Because they were attracted to the floodlights which were being turned on at dusk. And so now we're drawing all of these midges. Now I have to ask you, is the issue here dusk, which would be Mother Nature, it got dark? Or is it really a method issue because you're turning the lights on? So part of that has to be thought through before you can get to what is the real root cause. Usually, by the way, if you go through a 5 whys analysis, by the time you get to the 5th why, you're pretty close to what the root cause is. And that was the idea of doing this whole thing, is to try to get, rather than jump to a solution, which was, in this real case, that is exactly what happened. They started experimenting with different detergents. They started using insecticides, trying to kill the spiders. They put plastic owls up on the Jefferson Memorial, trying to chase away the pigeons. None of that worked because they weren't the root cause. This is an attempt to try to get at root cause, and a 5 whys analysis is a very easy and simple way to get there. So root cause, the lights being turned on at dusk are attracting midges to the memorial. That's the root cause. So if that is our root cause, let's run through it again. Our target condition was stop the need for frequent cleaning and concrete erosion by turning the lights on later at the memorial. Probably would not have been the first solution you jumped to, but in this case, actually adjusting the start and stop time for the floodlights solves the problem of the memorial eroding. So let's review. Why was the memorial crumbling? Because it was cleaned twice a week. Why was it cleaned so often? Because of the pigeons. Why were there so many pigeons? Because of the spiders. Why were there so many spiders? Because of the midges. Why were there so many midges? Because we turned the lights on. And as it turned out, the Jefferson Memorial was the first monument in Washington to turn on the floodlights. So any of the midges that were hatching from the reflecting pond in front of the memorial immediately went to that one. If they turned the lights on later, which is what exactly was what they tried or experimented with, they found all those midges went into the trees, and once they were in the trees, when the lights did come on, they didn't come back out of the trees. They stayed in the trees. So actually it solved the problem. Even after a lot of consulting time, consulting dollars, and a lot of other experiments, as it turns out, the root cause was simply turning the lights on later. So let's kind of use this same methodology to try to think about this water that's overflowing our sink, which we've identified in our case study today. So the problem, there is water on the floor. Keep asking until we think we get to a root cause. And this, I want you to think this through as I'm doing it, because there may be other answers that you think of, and you may go down a different path toward a root cause than what I'm going to show. So I want you to think a little bit out of the box here. Why is there water on the floor? Because the sink is overflowing. Why is it overflowing? Because the water is running from the fill valve. So we continue to fill and it's going to overflow the sink. Why is it running from the fill valve? Because the water shutoff failed. Well, that's in my case study, that's what we discovered. There could be other reasons for water or the fill valve malfunctioning or not functioning correctly, but in this particular case study, it's because the water shutoff failed. Why did the water shutoff fail? Because the shutoff valve is leaking. Why is it leaking from the valve? Because the rubber seal is worn out. So in this case study, in this example, I've kind of walked you through a 5 whys question here, and I end up because the rubber seal is worn out. We need to then somehow communicate that to everybody who's involved in this. And part of the way we do that is with a cause and effect diagram. I think Albert Einstein said it best: if I had an hour to solve a problem, I'd spend 55 minutes thinking about the problem. And if you remember, I said in that plan, do, check, act cycle, the Deming cycle that we're basing all of this on, the plan part of that takes up most of the time, takes up most of the effort. After you really have identified what the root cause is, you don't need a whole lot of time to try to figure out what you need to do to fix it or what you need to do to improve the situation. So spend a lot of time. Don't be afraid to spend a lot of time on why is something happening. So again, we start out with a problem statement, we studied the problem, and then finally we go to root cause. In our case, we did a 5 whys analysis to get to the root cause, and you'd want to put those 5 whys up there, display it as an Ishikawa diagram or a fishbone diagram. In our case, the faucet in disrepair is really the root cause of our problem. So we spent a lot of time over here to get to this root cause, and the reason we do that is so that when we get to the action part of this, we don't just keep shotgunning and trying to solve something by putting out fires, but we could have a very definite plan of how we are going to get the faucet repaired, but also how are we going to keep it in good repair. So the next step of this is called a target statement. And a target statement is a whole lot like the original problem statement, except now that you've studied this and you know a lot more about it, this problem statement is going to get revised over here to a target statement that is going to account for all the stuff we've learned about this problem. So again, it's where is it happening? My car. What is going to happen? It's going to be repaired. And how much? My mileage will increase to 20 miles per gallon. So that's my example. But in our case with the sink, what would that look like? Problem statement, study the problem, root cause, target statement. At the sink, repair the fill valve to reduce lost productive time. So we want to keep this focused on productive time. Another way of looking at this, for example, as a problem, because again, we're taking small bites out of a bigger problem, could have been a safety issue, not lost productive time. Or it could have been lost water or a utilities issue. So there's a lot of different problem statements that would have fit, but in our case, we focused on productive time. Once you've identified what the target statement is going to be, the next step is to identify what are the obstacles to prevent you from getting or achieving that target statement. In our case, you need to pick as many as make sense, but in our case, I think who can fix the broken valve is one obstacle. I don't know who that is or which department that is. We're going to have downtime to repair the broken valve, so that means we have to cut into production or stop production while the valve is being repaired. And we have to take more immediate action until we could achieve these things. How are we going to stop the overflow from happening immediately? How are we going to stop the problem immediately in the interim until we can attack the root cause and get it fixed for good? So developing solutions, and again, this goes back to that team atmosphere I was talking about a little while ago, is don't be afraid to make a mistake when you're experimenting with what the solutions are going to be. If we are too critical of people for choosing something that maybe didn't work, what we're going to do is then teach them not to reach or not to look for a better solution. So a lot of this comes back to that respect for people, respect for the people doing the work. And this is an example of somebody who had cases that had to be, this is an old story and an old picture, but these cases had to be closed, and then periodically the machine wouldn't close them, and they'd get caught on the control bar here. And this control bar also did a metal detector and did some other work, so it had to be close to the line. But as they came through, they would actually jam on here. So this was an A3 that the operators from this machine took on. And they didn't go to engineering and have engineering design something for them. What they did is they mocked up something actually out of a piece of cardboard and a 2x4 to see, would this work to prevent the jams? Their problem that they identified was jamming on this bar. So would this work so that it would prevent the unclosed box from closing? And what they found, indeed, it would slide up this ramp and jams just were eliminated. And when jams were eliminated, of course, productive time was dramatically increased. So after they mocked it up with duct tape and shipping tape and a piece of cardboard just to prove their point or to experiment with their solution, after they were satisfied with it, then they took it to engineering and said, could you design something like this for us? This is another creative inspiration, we call it, but this is another operator. This is a squeegee that was inside, I think, an airlock. And what they would do is these two holes were for mounting that squeegee, and the squeegee in an airlock has only a few thousandths that it needs to wear away before it's no longer performing correctly. So they would take these and toss them away and put a new one in. And one of the operators said, this end of the squeegee is still good. Why don't we just put 2 additional mounting holes in them, and instead of throwing them away, we'll just turn them around and use them the other way. Well, sure enough, they did, and this, like I said, goes back to 2017, but the net result of doing something very simple like this, which is an operator idea, ended up into a $14,000 cost savings, which is pretty impressive just in materials. Part of what we want to do is called pokeyoke. And pokeyoke is basically trying to say, how can we error-proof it so that it's never going to be done the wrong way? And one of the ways to do that, in this case, these are paint cans that are coming down a trough to a fill machine. And if the paint can, if this open end is flipped upside down and it's in this orientation, you can imagine what happens when it gets to the paint fill, because it's just going to squirt it on the bottom of the can and paint goes everywhere. So one of the operators had this idea, is why don't we just make a cutout so that if the can is flipped the wrong way, when it gets to that point, it just will get rejected, and if it's upright the way it should be, then it'll slide over this cutout and go to the fill machine. Something simple, easy, that indeed saved a lot for these folks. As I said, pokeyoke is basically looking at how can we mistake-proof something. And part of that entire thing is this. Errors are considered impossible to avoid. There is no one anywhere who hasn't made an error. Defects are what we're trying to eliminate. So if an error is made, you don't want that passed on to the next individual or the next process step. And again, there's good examples. A thumb drive can only go into your USB one way. Grounding plugs can only go into the receptacle the correct way. Diesel and gasoline are separated by different diameter nozzles. And you can get to a point where you put a metal detector in or invest in more sophisticated equipment to prevent defects from moving on. I need to skip this. I should have pulled this out, but this is a paperclip exercise that I'll suggest you try on your own at some point when you're in a team, is to write down how many different ideas you know of for using a paperclip other than being a paperclip, and have each individual in the team write down their ideas, and then compare all of those ideas or add up all of those ideas and find out how many ideas totally the team came up with versus how many ideas could any one individual come up with. Again, a good exercise for demonstrating the value of using teams. So this is another one, and this is just brainstorming. And there's 2 ways of doing this. One is to have a facilitator write down all the ideas and just keep putting them up on the board, because there is no bad idea. Whatever the ideas are, you write them down and you capture them. Another way of doing this is, especially if you have an individual in the room who maybe is dominating the conversation, is to have individuals actually write their ideas on the Post-it notes and post them on the wall. Another good way of doing it. But after you have all these ideas, how do you begin separating them? And typically what you'll find is all of those ideas are going to have an overriding common theme. And using an affinity diagram of putting all of the ideas under what this idea is, you'll find that a lot of them are very similar, even though they're different. So using an affinity diagram allows you to take a whole bunch of ideas and start putting them into groups of what we would do to solve those issues. Catchball is another way of doing it, and this is to send out an idea. Whoever had the idea is fine, but then you go around the table and keep working on that one idea. You can expand on the existing idea. When it's your turn, you could change the idea. However it makes most sense to you. But this gets you, again, getting a lot of ideas on the table, a lot of potential solutions to what we're trying to do, or potential experiments to achieve what we want to achieve. 5 W's and 1 H, systematic questioning called the Socratic method. Is this step necessary? Should it be done? When should it be done? Where? Who? And I guess my favorite quote in all of manufacturing, and I've been doing this for a long time as a manufacturing engineer or technically involved in a lot of aspects, is, in my opinion, and Peter Drucker wrote this 1911, I think, there is nothing so useless as doing efficiently something that should not be done at all. And quite often people do that in office atmospheres or in manufacturing, where something that really shouldn't even be done, it should be replaced by something else, we begin automating it so we could do it all the faster. And it's just, as the quote says, there is nothing so useless as automating something that shouldn't be done at all. So working through these questions makes a lot of sense every time you're doing an A3. So once you get all of these Post-it notes or all these ideas, now you have a team. So the team now has to agree on what do we do first, what do we do second. This is a great tool for prioritizing those ideas. And simply by using those same Post-it notes on a grid like this with a team, identify which are those ideas that are going to be most effective, and identify which of those ideas are going to be easiest to implement. In quadrant 1, you're going to end up with those things that are relatively easy to do and are going to be most effective at solving the problem. In quadrant number 2, they're going to be a little harder to do, but still very effective at solving the problem. Quadrant 3, I don't know. Now they're relatively easy to do, but there's not a big impact out of them. And you're going to have some that fall into quadrant 4. Quadrant 4 they're very difficult to do, and they're not going to really do much to solve our problem. I'll suggest to you anything that ends up in quadrant 4, maybe you just want to pull out and not do. Kill those ideas. Don't be afraid of killing ideas if they're not going to be effective and they're very difficult and time-consuming to do. But those that are in quadrant 1, which are easy to do and very effective, they may become your just do it items. You know, these are very easy to do, they're going to be very effective, just do them. Don't do a whole lot of anguish over them. And then between quadrant 2 and 3, these become something that now you have to rank as to what you're going to do first, second, and third. The value of using this tool is that you've now brought the team together in consensus of what they want to do and how they want to do it, because you want team buy-in, and this allows you to get that team buy-in. So once you have those ideas, now it's a problem, what's the countermeasure, who's going to do it, when are they going to do it, and what do we expect, or what did we learn after we've done it. So in our case, first obstacle we had is immediate improvement. If you remember those obstacles that we had on the A3. Instruct all operators to shut off the valve manually. Who's going to do that? Well, it's name C. Let's say it's the supervisor. They're going to do this by January 1st. And then after they've done that, the question is, what happened? Well, we improved the downtime by 50%, but we still have downtime. And the new current condition or the next obstacle is how do we get it repaired so that we don't have to lose that 50%. So who can fix it? Submit a repair order to maintenance. Who's going to take care of that? Name A. That could be anybody in the department who knows how to fill out a work order. They're going to do that at the same time you're telling the operators to do this. Maintenance will repair. And after this, new current condition, we need to schedule the repair. So when can it get fixed? Schedule the downtime on the machine for the repair. That could be done by the supervisor or someone else again. Probably in this case, it was a week later. We're going to schedule for that. Improve. The result of this is we expect 100% improvement or elimination of all the downtime. And how do we sustain it now? That becomes the next obstacle. Sustain, add to the preventive maintenance program. Who's going to do that? Probably back to the supervisor. Target completion February 1st, and then monthly check and tighten. Maintenance, zero overflows. By doing it one step at a time, it's called single variable experiments rather than shotgunning and doing all of these things at the same time. Quite often, shotgun approaches result in a lot of wasted effort, a lot of wasted time. Problem statement, study the problem, root cause, target statement, obstacles up here, and then finally our experimental actions. We populate all that and again post that A3 on the community board or communication board so that everybody is involved. The next step is going to be how do we check? Again, this was all plan, do, now we need to check, PDCA cycle. So again, you're going to go back to check sheets and something very visual. And when we collect the information again, we again have a Pareto chart which can show us the data. In this case, we've reduced the lost time at the sink from what we started, I believe, at 123 minutes or so. Now we're down to 19 minutes in this case study. So this, while this is a good visual display, in our case on an A3, one of the things that really typically is valuable is to do a before and after. What were the metrics before and what were the metrics after? Because if you could display that, that means a lot to people. That means a lot to management, and it means a lot to the people who are doing the budget. If they can see what were the physical differences, it means a lot. So in this case, again, problem statement, study, root cause, target, experimental actions, results. And post those results. Make them very well known and communicate it to everybody who's involved with that. Standardization and sustain. So if we were able to do this, and this is some pretty phenomenal improvements, but if you were able to accomplish that, how do you keep it from backsliding? How do you keep it from going back to where it was? And standardization and sustaining is something that we all need to think about and how we do it. It provides a way to measure the performance. This is one way to do it. It's a piece of standard work which basically tells the operator what they should be doing, why they should be doing it, and also shows it pictorially so that someone can easily look at this and follow this, which is add detergent to dispenser, fill the tank, adjust water pressure, clean the screen top to bottom, hang the screen to dry, and check water level and detergent in the sink. And if we do this sequence of operations, it means every screen we do, we're going to check this water level and probably in itself minimize or very, very quickly detect if it's not being done correctly. And every 100 screens or so, we should be checking the quality of the solution. So this is step 7, standardize and sustain. What actions are needed by the operators, the suppliers, the support areas, management, and who and when will it be complete? So now we have a complete A3, a problem statement, a study, a root cause, target, actions or experiments that we performed. And by the way, I said earlier, we need to be tolerant of mistakes. Not every A3 that you perform or that the people on the floor would perform are going to be huge successes. Some of them aren't. Some of them don't work out. And that's where management needs to step in and help the people out. Don't let them out there in a vacuum or on a limb. You need to work with them. Check the results, and then finally, how do you sustain it? I like standard work, but there are other ways to sustain things. This is a typical communication board. You've heard me mention communication board. This was very useful for this company because it told you what were the completed projects, told you what were the projects presently actively being worked on, and then in the middle section of this communication board, it allowed anybody to come up with a new idea for improvement or a new opportunity or a new problem. This particular group also kept tally of what were the results of the projects they worked on so that they had a quantitative value or a quantitative savings for each of the problems, each of the A3s that were worked on. This is a typical A3 format, and again, it's just following the plan, do, check, act cycle, but you'll find I also have the DMAIC from Six Sigma, the DMAIC descriptions in here as well, because they fit in with plan, do, check, act. They're almost the same thing. So again, let's get started. Think of a problem statement, and the problem statement is going to be where is it happening, what is happening, and how much is it happening. So I'll leave you with that, and you can entertain any of your own problem statements or opportunities. And with that, we're kind of at the end of this. I'm not sure if there's any questions that we have. We do. But we're... The question is, there an ideal team size for problem solving? My answer is, I would not have a 10-person team, because when you get to the point where you have to make consensus decisions, it's hard to get 10 people to have consensus. I personally like 3 or 4 people on a team. I think it's most effective and most impactful. Another? All right, the first question is it possible to have more than one root cause? And I have had occasions where there are multiple causes, and some of them have more importance than the other, and neither one of them actually were the root cause, but both of them were very, very telling in which direction you had to work on to reduce the problem. But there are times when you won't get to the actual root cause. And again, my definition of root cause is once you get there, you've totally eliminated the problem and it never resurfaces. What we find is a lot of times we only get 95% of the problem solved, and that other 5% is being caused by something that we really hadn't even considered. But then there's a little bit of the effort and diminishing returns. If you've reduced the problem by 95%, how much additional effort do we need to keep putting into it, or are there other things we should focus on? And I'm sorry, what was the second part of that question?
Who is responsible to work on that problem?
Who is responsible to work on the problem? I personally like the operators from the floor to be the people working on the problem or trying to solve the problem, but quite often they will need support from management, whether that's the supervisor, plant manager, or purchasing, and there needs to be some management involvement to help them knock down some of those barriers so that people will work with them to get it solved. But if you can get the people on the floor who are directly affected by the problem to solve the problem. They then own it, and then they are happy to make it work. One more.
How do you address a recurring issue that management has not fixed, yet everyone knows is an issue?
Ouch. How do you handle a problem or a recurring problem that management is aware of but just doesn't fix? Part of that is to identify maybe a new problem, and that new problem may be, why does management not want to address this issue? Sometimes it's financial, sometimes it's they're just not convinced because of the data that was collected. But what you do need to do is identify why somebody doesn't want to fix something that's been proven to be the issue. Usually management is more than happy to resolve any of those issues because they directly relate to cost savings and efficiency for the business. So I'm not sure I'm helping you there, but maybe take on a new A3. Why is management not fixing this issue? So I think that's it. Again, my name and address is on this last slide. So if you have any questions that you'd like to email me, feel free. I'd be happy to address them on a more personal basis. With that, I thank you for your time and attention, and I hope you all have a good day. Thank you.